Hello, SB6GK here. Today I would like to show you how to simulate a low-pass filter in Microwave Office. You can treat this tutorial as a first introduction to Microwave Office so that the further tutorials with more advanced topics will be more understandable. And I would especially recommend this watching to amateur radio operators and students who have access to Microwave Office, because if you have a university email, you can actually use the Microwave Office for free, at least for 6 months. So that's actually a very, very good deal to get some useful skills and to advance your projects to the next level. This is a very powerful tool, but we will start with something simple, but of course very useful. So select this filter synthesis tool from a wizards, and you can see that you have synthesis for lumped elements for your filter and matching networks also here. We might talk about them later, but today we'll go to the design, which actually will show us the dimensions of a microstrip component. So basically pieces of copper and transmission lines on a PCB substrate. So we will design a low-pass filter using the microstrip realization. You can also calculate the lumped element like coils and capacitors as a single components, but this will use the distributed components. So basically, copper elements on a PCB will act as a as an inductor and capacitors. Let's go for a distributed stubs. Those can be a little bit smaller than the stepped impedance. Also, there's this function that you can compare the sizes of elements. I will turn off some of them. And I didn't choose what frequencies and so on I want, but if you look, for example, for this two filters, you can see how different space they will occupy. So this is just some useful tool that you can use. But let's move on with a single radial stubs. Click here. I will move this window a little bit to the center because I don't know why it wasn't maximized here. So let's focus on here. So first, you need to define what your PCB substrate is on, because this of course uses your PCB as a method of achieving this capacitance and inductance. So go to the design option and the technology tab, and I will be using a FR4 substrate, which is very cheap, but maybe not the best for higher frequencies. We will stay with something that can be physically measured at home. So I will try to keep it below 5 gigahertz. So let's put here 4.4 as an so this is our dielectric constant, and the loss tangent I will put at 0.03. This is what Wikipedia gives for a FR4, so most popular substrate, most popular dielectric for our PCBs. And the conductor thickness is a typical 0.035 millimeters. I will not change this. This is 35 micrometers, which you can meet on a GLC PCB website, for example. And the height of a board is very, very important factor. Most of the PCBs that you meet will be probably 1.6 millimeters so far, but with lower board you can actually achieve thinner 50 ohm traces. So the impedance of a trace on a microstrip technology will be defined especially by this height of the dielectric between your layers. Your bottom will be the ground and your top will be your signal conductor, right? So with a 1.6 millimeter, this you can actually see right here, because it has some calculation given for us. For 1.6 millimeters, this will be a 3 millimeter thick trace. This is very thick. For 1.2, we are talking about 2.4, I think, 2.28, so close enough. If you have a special substrate with 0.6 millimeters, this will be about 1.13, right? So this is something that I have at home that I can etch using some chemical solutions. So I will stay with this 0.6, but if you are ordering PCBs, check that this option is not prohibitively expensive, because it might be. From JLC, I've ordered PCBs that were 1.2 millimeters. So maybe let's I will keep it 0.6 because I think I will be able to demonstrate something. But if you are ordering, keep in mind what you are using. Now, you can also go to limits and set up what you can etch and what you can order from your PCB manufacturer, because some of the things might not be possible in real life, but they are always possible in simulation. So keep track of that. Right. So first, maybe let's look what specification that we have, and I will design this filter for, let's say, 1.5 gigahertz, so something rather low, relatively speaking. And you can see that this few buttons change to red. So why is that? So you can see that this is our schematic, and the schematic is of course working correctly. This is our pi structure of this filter of the sixth order of a Chebyshev, and you can see that it's calculating it correctly. This looks like a low pass filter indeed, but this is your physical structure, and you can see that there's a problem with those inductors here because these thin traces have a higher impedance than these white traces, so they act as coils especially, not because they are coiled, but because of a higher impedance that they present for these frequencies. And these radial stubs, these triangular looking things, they are like a capacitors, but also as a stub, because if you have stub with certain length, they will present a very low impedance, so basically there will be a short at this frequency. But either way, if you click here, this is a very important tip that I like to use. You will see the dimensions. These are in millimeters, but if you go to the environment options, you can press, for example, the inch and click apply. You will see those in freedom units, but I use what everybody else is using, so let's stay with millimeters. And you can of course select other options. I will maybe right now change to the picofarads because in microwave we usually don't use microfarads. We stick with nano and pico usually, so this is something that you might also want to change. So yeah, right. So what's the issue? If you go here, you can see the description of this filter using the names that are used later on in the schematics drawings for the microwave office, and you can see that the length to the width ratio, oh sorry, the width to the length ratio is too low, so this might be very difficult to manufacture, right? Okay, so how do we change it? So for example, you can go and change the polynomial of your function of your filter. I will switch to elliptic, which will have much steeper slope of attenuation, but the stop band, you can see the stop band is not very high. There will be some leakage that we can expect, right? So this region is very nice actually, but later on it degrades very quickly. But this is just a tutorial which I want to show you. If you are, designing a real system as an engineer, you have to of course choose what suits the best your application. Maybe you want to eliminate the harmonic of 1.2 gigahertz. Then this filter might be very good for that, right? If you care about the good return loss, so your reflections, this is quite a good solution, right? But some filters might be not so great. Let's check what happens here. So this actually quite good, but something that is also worth checking is, let's say, for example, this return loss might be not very favorable, right? And also the realization is not possible. I will switch to elliptic. We'll stay with that. What might be the problem is that this high impedance, these traces, they will be very, very narrow. So if you are trying to make this at home, you have to check if you can really make something so thin. These are of course 50 ohm traces, so they are much wider. Right. Let's go then later on. You can see that description of parts, but I usually prefer this view. So what I will do is I will use the snipping tool, and just as a some sort of copy and pasting method, I will be able to remember these lengths. So let's click generate the design, and I will call this the LPF 1500, let's say, and the span of the frequencies I will set it from, for example, 100, let's say 1 gigahertz up to 10 gigahertz. Maybe that's too much, but 5 gigahertz for example, and I will settle down for 401 points. All right. This is not super crucial for us because I will show you how to set up our simulation of closed form using just custom, maybe not custom, but doing this manually. So we'll save this, and you can see there's a nice plot already prepared for us. And this, if you look here, we have no layout of the structure. This is the layout button. It's empty because you are using just this distributed stub filter in this representation of a maybe not lumped components, but as a schematic, right? So this is quite simple simulation, and it's very idealistic. It doesn't take into effect many of the electromagnetic effects and that will happen on the microstrip, right? So this is not super interesting for us, at least now. We can compare this later on, but something that I would like to show you, and you can see it's saved here, is let's start a new schematic with the LPF 1500. I will call it closed form, so closed, doesn't matter. There are some rules to creating this name. You cannot start with a number, I think, but you will probably run into this at some point. Let's open the element menu and add msub. So this is the definition of a microstrip substrate. This is very important, and you have to remember about it when you start the project, because all the other elements will be assigned to this definition of a substrate. So if you're not sure what those things here name, because these are quite, ambiguous at the beginning, you can click this double click on the substrate icon, and you can see actually description here. So let's start with this. This is of course the dielectric constant, so we set it as a 4.4. The height of the PCB is 0.6 millimeters. The thickness of our conductor is 0.035 millimeters, so 35 micron. And this actually component is relative resistivity of our conductors to gold, because in microwave office the ideal conductor, let's say, is treated as a gold. So how the simulation will actually know how to compute these losses and so on is that you have to set up certain number here. So what this number is, if we use copper, let's go to tools and the TX line or the transmission line tool. Now this looks very primitive by 2024, which is when I record this, of course, but it's actually a very powerful and very handy tool. So here, let's scroll down to copper. Copper, as you can see, it has a conductivity of 5.88 Siemens per meter. Compare that to gold, which is 4.1. So what you are going to do is you're going to pop up the calculator, and you will learn this number later on. But first I want to show you how I derive this. So let's just put 4.1. So this is the gold to copper, which is divided by 5.88. Now you got this 0.6972. I will just copy the first four numbers and put this as this relative number, of course, 0 point. Okay, next is our tangent loss of a dielectric, which is 0.03 in our case, and the dielectric normalized contrast, I will put this as 4.4 as well. So great, we have the substrate set up. I will save the projects, for example, here as a tutorial 1, all right? Yeah, that will be enough. After saving the project, we'll continue with some basic setup. So let's go to the project options and click edit. you can see this is the frequency range. So normally this first range that we set up, it didn't move over to these settings. So I will start it once again. Let's say, let's go maybe a little bit further. Let's go from 100 megahertz up to 5 gigahertz. Or maybe let's, to keep it even, let's go from 50 megahertz. That's too small. 500 megahertz to 5 gigahertz. I should probably think it this over previously with step of 10 megahertz, for example. Click apply. And you can see 451 points. Well, I am on a laptop, so this is quite a lot. So let's go for almost 100 points, 91. So we have something in the middle. Great. Also, here you have a global units tab, and if you go to edit units, you can also change this capacitance to picofarads, nanohenries, and so on, your units, and this is quite useful. Okay, great. So let's check we have this set up correctly. Let's hit OK. Now we have almost everything that we need to start drawing the schematics, and we'll begin with ports. So these are the 50 ohm ports by default. Let's place them. Now, in sorry for that. You will have to rotate this port. So let's go to the, or you can also flip them, right? Maybe this is not the most, this is not the most convenient feature of this software, but you can flip or rotate these components, right? If you ever used ORCAD, you are probably familiar with this feature. It's not great, but nowadays standard, but we'll do with that. Next, since we are aiming for something physical, let's add 50 ohm traces that will be put close to these connectors, which these ports, sorry, which you can also treat as a connectors, right? So I will copy and paste this here. Length is okay, but the width, here you can set the width, and we're not going to set everything manually, because if we want to change this in the future, then we'll run into some troubles, of course, by changing everything in our schematic. So if you press Ctrl and E, you will see this small box appearing. This is a text. So let's say that W0 is our standard width of a 50 ohm trace, and you can just treat it as a variable. So let's put maybe the snipping tool here, working with a relatively small screen here. W0 is 1.1, sorry, 1.138. Great. Just please press Shift and Enter to go to the new line. And we'll go to W1, which is our high impedance trace, which acts as an inductor here. Is 0.14, and you can see that this is the only two widths that we need. Then we go to the length 1, which is 7.706. Usually don't need to be that precise, but just to be safe. Then we will go to the L2, which is 5.366. There's also L3, which is 9.781. We will tune this later on anyway, so really I'm building here too precise, I would say 8.461. And finally we have L5, which is 2.681. Great. Now radii of the radial stubs. 7.209, R2 is 9.071, and R3 is, of course, 7.187. You can probably copy this from your previous design over here, but I want to show you how to start from complete beginning and from complete scratch, of course, with only the synthesis and some, if you run, for example, you want to design some hybrid or divider, then you can just put your parameters like this and then start drawing the circuit or the schematics capture. So, okay, we have this. Now I will also add something that will be our frequency tuning parameter. So let's call it, for example, scale, and I will put it to 1.0 at the beginning. You will see later on how to use this. Great. So keep in mind that we have to design something like this. So how we go about that? So first, here I will just put this maybe length. We'll try to select this length and add this as a 10 plus, because you also can use the equations here as a plus L1, and here go, for example, with 10 plus L1. Okay. Now if you go to the layout, you can actually see these traces, and if I hit the measure or this yardstick, you can see it's 17.706, so it works great. Now let's zoom out and move this further on because we need some more space. Let's add another emlyn, so this will be our thinner trace. So this, as you probably accept, will be the W1. I just realized I forgot to change this as to W0. So this will be, of course, a lower letter W0 with the length of a L1, sorry, L2. One's capital and one is smaller. So this is quite confusing here, but we can manage, I think. Now, how do you approach this radial stub here? Well, you can search, of course, here for a radial stub, but if you don't know the exact name, you can, of course, search for a description of a radial stub, and we want to have a radial stub on a microwave substrate, right? So this is the double radial stub, so this is like a bow tie. This is for series and shunt. So we will go, and there is also another way of doing this, but we'll go with this component. You can see that this is our stub, and something that gives you more freedom is actually going for a M cross. This is like a, as the name implies, cross that acts as a junction, sort of, that allows you connecting multiple components together on this microwave substrate. So let's put it here. So the cross, of course, will have 4 widths at each of the junction point, and this will be the W0 width, of course. I will copy the W0 and place it everywhere. So if you want to do double radial stub, you can of course put another radial stub here. But if you have open connection for a simulation purposes, I will actually look for something that is called mopen. So this should probably this should properly close this junction here. Not super critical from what I've checked, but it's nice to let everyone know that, hey, there's nothing connected here. It's not that I forgot, but you know, everything is nice and tidy here. And put, of course, W0. Of course, if only I could spell, that would be great too. So let's go also here W0. Now, what is the width of the radial stub is basically this base here, how it will adjust to the junction point. Now, for the radius, of course, we put R1. Now, this was quite a lot of work, to be honest, not that I'm that lazy, but if you go to the radial, sorry, not that. If you go once again, let's delete this name and now search by the radial stub. There are radial stubs that allow you to place, not this one, that allowed you to put already component that has both this T junction and this radial stub adjusted to it. So you can use either one of them. Just pay attention if you choose the components that for the microwave substrate, they have definition of M-sub, and this M-sub is linked to your N-sub that we have defined before. If you double click, you can see it here. If you didn't define it before, you would have to change this definition here. But that's what it's important to remember this at the beginning of the schematic capture. So let's go for another length of a higher impedance trace. So this will have this 9 millimeter length, and then we will have another M sub sorry, another, you know what, let's go, sorry, let's go maybe with, just as an illustration, of course, we want this shunt here. Let's go with this, maybe we'll play with this a little bit. So this will have, of course, the radius too. Now the W, G and W, so the W is the width of this trace, so this is the W0, and this is of course this base. Now you might want to make this notch here a little bit wider in order to allow easier manufacturing if the W0 is too small, but I will stay with this because I can manage that. Just change the length. The length will be L3 here, not L2. Yes, almost got it this time. And there's of course two of them, if I remember correctly. It's someone symmetrical. No, it's actually L4. So this will be the L4. A small difference, but it's quite important to focus on those details. Almost there, 2/3 way in, I would say. R2 is set up, yes it is. And so we need another radial stub. Now we will place this. Now I will copy this and rotate this. I'm sorry that I'm confusing the shortcuts, but I was using the Altium before and some of the shortcuts don't carry over between the programs, which is of course always annoying. So we want to set up here the radius number 3. The W0 is actually set up. There's another thin trace if I remember correctly. Yes, it is. So this will be our last, the L5, quite short little one. Now, there's one component that might come in handy if you are working with much higher frequencies and the difference in the widths of the components. Actually, some people recommend this in electromagnetic simulation to terminate every change step of the width. I will not do this here, but if you want to be really academically correct about this and so on, there is something that is called the tapper. I've read in some application notes that actually you should use this in when you connect, for example, the transistors to a substrate, and you want to be sure that everything is going well. There is something like this, and you can see that it's changing the width between different traces. But we'll skip over this, over the tappers. So it looks like we are practically done here. Everything seems to be set up. So let's see how our layout looks, because sometimes we can get some surprises with that. So press this layout button over here. Now I will press Ctrl and A. So select all, and then we'll have snap together. And seems like it works correct, although the width might be incorrect. So let's check. Yeah, here we should have W0, and of course, as you can see, I should have put the W1 here. So again, pay attention to this and you should be golden. So let's just painstakingly change everything. This is of course everything doing live so that we can catch stuff like this. W1, this is also W1, and this is W1. I will save it, Ctrl S, and let's check again. Yeah, it's much thinner, and we are okay. Now I will set also the angle of this radial stub. Uh, I think 90 degrees we can allow here 19 degrees. Okay, looks nice. And here I think we already have like the 90 by default, right? So this angle should allow us to be a reasonable broad bandwidth of the stubs, but of course we'll see how that behaves later on. And the fun of it is that you can very simply change these parameters and see how the circuit behaves without actually, making something physical. Right. So we have ready structure and we are already very close to simulating it in a closed form. But first, let's add some graphs. So go to the graph folder and create new graph. Select rectangular and we will name this 1500. I don't think I can stay with the name, so maybe LPF 1500 closed form. Now I like adding these underscores, but I don't think it is actually that necessary here. But in the file names, usually it's easier to process them if you don't want to account for white spaces. So that's my behavior here. I will add measurement. This is very important to understand. Select the dB because we want to use this logarithmic scale in the ERF word. Now select your documents with the closed form simulation. So this is your data source. You can see that the sweep frequency is correct for the x-axis, and we start with the port number 1 to port number 2 at this measurement. This is in the S measurement, so this is your scattering parameters or the scattering matrix parameters. This is in port selection. You can see there's really a lot of them, but for purpose of this microstrip, we care mainly about the port parameters and maybe in a circle about the Smith chart. But this will be used with the Smith chart, not with the other measurement type. Anyway, let's add S21 because this is from port 1 to 2, and add also the reflection of port 1 to 1. So this is S11. S22 should be ideally the same as the S11 in this case. So let's close. I will move this a little bit on the side, maybe not the best looking example, but we'll go with it. So the moment of truth, if we made any mistake, let's click this analyze. And it seems like we are correct. It's finished status, everything seems to be correct here, so we will close this. And you can see we have this LPF, so works like a charm, I would say. Now I will show you some actually features that I like in the graph. So this is our closed form simulation. Let's add options. Now you can see we have the axis, and in the measurement tab, I usually like to go to the S11, press right. So now our reflection is taken on the right scale. So there's a little bit more dynamic range usually to the other measurement then. And this is something that you will often see in the data sheets. That's the reflection is on your right and the insertion loss is on the left. So this is quite nice, but we need to add the labels because otherwise we don't know which one is which. Usually you can deduce this, but so the left is S21 and I will add the unit dB, although I'm not sure if it will not show us the unit by default. No, okay, it's fine. We have S21 in dB. The right axis is the S11 in dB. I also don't understand why it did actually put the megahertz, but it uses the brackets. I prefer the square brackets for this, but you can change of course the default, the label and so on, but I think we can stay with this. You can of course adjust the fonts and the colors. So if I wanted to swap these colors, for example, I think usually I'm using this in a different order, so I will do this here. If you intend to print them, you can also use the dashed lines, for example, and use the markers to differentiate many lines. Also the thickness of the line, for example, we can increase them. So this is quite handy, of course, but I think everyone can use something like this. Of course, there are also the automatic markers and the markers overall. So I will add marker, for example, and I want to show you that the point -3 dB is here. So you can do this by hand, but you can actually search for some specific points. So for example, if I add automatic market search and I want to find the point of minimum S11, for example, for a tuning, I can just press on this line and it will show me where the minimum reflection occurs. So this is quite handy. Of course, you can also use this for a maximum and so on. And you can also use this for specific values. So you can see how that works. Very, very handy. Of course, you can also change the axis in the previous options, but this is, I think, quite nice, quite better plot than we have seen previously. You can see the 50 dB, so quite strong attenuation is about at 2.5 gigahertz, and the losses in the passband are about -1 to 1.5 dB, I would say. So not the worst filter, but this is a closed form. This doesn't really take into account that there might be some coupling between these two elements, and some losses along this. I mean, it takes clearly the losses, but maybe how these fields interact between each other. This is not really taken into account here. So in the future video, I will show you how to transform this schematic into the electromagnetic simulation schematic, which will take us more time to compute, but will give you probably more accurate expectations of what will be your measurements. So thank you very much for watching. If you are interested, then stick to the series, and I will show you some more tips that you can apply to your projects. Thanks for watching.